Al-Kawi kesenuan. Abdurrahman kesenuan. time to do something. Okay, let's go. I have prepared, good morning, a small demo for today. Where am I? Second, I'll turn. This way. Yeah. I have a small demo for today. We already saw this device. It's analyzer of amplitude frequency characteristics or border plots. What's inside? Generator of sawtooth-like voltage which controls AC generator by frequency. Here we have output, it's so-called switch generator. Frequency will change time frequency. Up, up, up, down. Up, up, up, down. This voltage also used to plot a research figure for the X, for the horizontal movement. Output is stabilized. Object under test. Absolute value and Y channel. As a result, we have a research figure being on the horizontal frequency, on the vertical, amplitude of transfer function of our test object. It's how this border plotter, let's say, works. But I will use one of its features for my demonstration. It has ability to put on a Y, say the resistance, and some function, signal from the external source. I can add signal from this external generator to the channel of vertical deflection. Without, I don't have this circuit now. I only see some result of interference between switch generator and my outer generator. We will see a chart where on horizontal will be frequency the same, and on vertical will be signal of the switch generator plus signal from external generator. Without the circuit, I'll see only, let's say, interference effect light is disturbed this way and No. Oh, here it is. Closer. Here it is on horizontal line. I'm changing frequency of the output generator. It's swing 21 megahertz, 20.2, it's in fact 20.8. So the whole scale is some 500 kilohertz now, approximately. You can see I'm changing the frequency of the external generator. What we see, this green, I can make it bigger and I can amplify it. Yeah. It's an interference voltage of a difference, as a function of frequency. To see the whole range. Let's see. This margin, where my 20.4 and this margin 20.8. So we have 400 kilohertz, whole scale. Whole screen now 400 kilohertz. Yeah. Maybe I can get a bit sharper. It is it. Light. 1 second. Where? Why everything you need disappears? I need a very scientific, very scientific instrument. One second, we will get it. Extremely scientific instrument. Yeah. Here it is. Yeah, we see interference product as a function of frequency. We have drop at the DC regime. It's because of system frequency chart. But the idea faster, something like this, and approximately 400 kilohertz. One second, I'll compress the time scale. A bit compressed. What this experiment proves? We have pair of coherent signals. They are coherent. They are some. Result, the interference product exists. They are coherent, so we will have result of interference. But if we analyze it in frequency range, okay, we have something like this decaying. Width, okay, approximately, now I have 400 kilohertz. This means, what outside this 400 kilohertz band, they are not disturbing each other. Yes, they are coherent, they are interferent, but the energy of interference is, let's say, concentrated or located in the limited frequency range. I can have, let's say, 20 megahertz. Guard zone, this will be 20.4. Let's say safety 20. At a 21 plus it will be 20.6. Next guard zone 21.4. This zone is occupied. I can use it. Any signal within this zone or 9.6. Any signal within this zone will interfere with let's say 20 megahertz. But outside, if I have signals at 20 and 21, they can coexist without any problem. They are not disturbing each other. See, the result of interference occupies some 400 kilohertz. Outside the zone, there will be no significant disturbance. In fact, I can use without problem. If 20 megahertz is occupied, 21 actually is free. I can use it. I can create kind of frequency scale or frequency net. 20, 21, 22, and so on. They are a signal at 20 will not disturb 21 until I have this 800, 400 each zone where disturbance exists, but outside I can use it. For example, coaxial cable. Its frequency range is up to 2 gigahertz. I can take this 2 gigahertz and split it as a frequency channels. Just understanding what, for example, speech needs only 3.1 kilohertz. Looks very attractive. I can split this gigahertz into many voice channels, or less data channels. Telegraph, Morse alphabet, requires only 300 hertz. I can split gigahertz in millions of telegraph channels. One only question. I have, let's say 20 or 21 megahertz, it will be carrier. I can have, let's say, 1 cosine 20, and it's this one. This one will be cosine 21, 22, and so on. Carriers, carrier frequencies, independent frequencies, they are not disturbing each other. And I have my information, voice, data, or something. That's a problem I need to solve. I need to find a way to pack my information into this cosine or sine signal or modulate it. It will be transferred to the receiving end via, let's say, radio channel or cable channel, or in power engineering, there was technique used. Take high voltage line, put a resonance contour with frequency approximately 100 kilohertz. It's a filter to prevent high frequency signal from leaking out of line. And with the help, I can eject signal at 100 kilohertz. And on the remote side, I want to eject signal and receive signal here. So-called power line carrier. I can use the same technique on high voltage line. Such technique was used for line protection to transmit current direction. If currents on both sides are, let's say, like this, it's okay. Or like that, it's also okay. But if both currents are directed inside, it's obviously a fault. We need to disconnect the line. Also, frequency separation technique. Now, question, how can I put information on a carrier and extract from the carrier? I have a carrier signal, let's say, maximum cosine omega 0 plus phi 0. Carrier signal. In our example, 20, 21, 22 megahertz and so on. I want to transfer, let's say, it may be voice, or state of the current. Why not? At this moment it's not important. What can I do? I can use, create, for example, this way. S0 1 plus. Okay, easy. Cosine omega I can use an amplitude of carrier to transfer my information. It's easy. Take amplifier with controlled gain, controls our information, and you get what? Amplitude modulated signal. Amplitude modulation. We can use signal amplitude to let's say as a way to place our information. It's the easiest way. The first reliable technology used amplitude, but quality wasn't best. We can do this way. One plus m. M is a modulation index or modulation depth. Constant. Omega 0. We can change frequency. Use a frequency to put information. It will be frequency modulation. Or plus 1 plus n. We can change only angle. It will be phase modulation here. We can change frequency, it will be frequency modulation, or they're very similar. We can only modulate angle. It will be phase modulation. Need a data transfer. For example, this 0, 1, 0, 0, 1, 1, 1. Mark each quadrant as a binary. This can be achieved via phase modulation. Need more dense data flux. For example, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, and 1, 0, 1. We can use schematic like this, changing both amplitude and angle. All kinds of diagrams are quadrature modulation. For data transfer, now most popular are quadrature techniques, when both amplitude and phase are used. Let's start from something simple. amplitude modulation is a simpler one.
So amplitude modulation and frequency modulation, when you demodulate, you get
what I put in. If it was, let's say, voice, I'll get voice. Data, okay, I'll get the data flows. Usually, the older version, where analog, where only voice or some basic data were used. Okay, let's more the alphabet. It can be used for numerical information. In modern system, it's a layer. Base layer use some carrier, and carrier is modulated with some, let's say, better use word stream. It can be or digitalized voice, or sound, or date, not important. It's a layer abstraction. We have upper, it's a media. It can be cable infrastructure or, let's say, a radio network. It's a medium. For medium, it's not important what we transfer. The only case your frequency band, use it. We prepare for transmit of some kind of signal. We need to pick our date. We are not interested what on at this moment. It's not important what on upper level. We just have a stream. We perform a modulation and we transfer a stream to our recipients. At the upper level, we need to create a stream. I don't know. It may be, for example, voltage and current measurements. We digitalize them. We compress to save. Let's say, to use infrastructure more effectively. And we need to put them in a stream. Usually it's a data plus date itself plus some additional redundant information allowing to check data integrity. Because channel is not safe 100%. So it's the way how stream is created. And we also have an application level. For application level, it's not important what's below, but application level needs to create a stream. Okay, let's check something. Let's take, for example, something simple. Very simple voice communication, analog. In fact, it's easiest to create. Data channels are much more complex. Yeah, what I need an amplitude modulated signal to analyze. The first idea, let's say, frequency channeling. What we can divide our medium, it's not any environment where harmonic signal or any signal can propagate. We can split it into set of frequency channels because we have a coherent signal, but the mutual coupling effects are limited in a frequency. That means what with the safeguard zones we can slice whole. It may be air, it may be cable, it may be power line into frequency slots, and at which frequency channel we will set a let's say system of channels. At each frequency, each channel is in fact independent, and we can put what we need to transfer independently on each channel. We can use part of channels indirect transfer and part of channels for return. Easy. I need an AM generator. 1 second, I'll bring it. I need modulated signal. In theory, I can use this one too. It's also capable of amplitude modulation, but use lower frequency. The 8 kilos of signal. 8 kilos. Anyway, get me the smaller one. Model 42, model 44. Big difference. Appears with let's say design unleashed his fantasy. Into model growing this to this. Don't have replacement. Okay, what signal. Where is my second. Oh. Come on. Okay, something like this. Yeah, what I got here. This watch generator produce sine at a frequency 1 kilohertz. I put it as a boolean. Here it is, signal from the watch generator. Pure sine. So we have source 1 kilohertz. It's our uno. Very simple information. What I can do, for example, here it is. 100 kilohertz. I have source 0 with the frequency 100 kilohertz. It's inside this generator. And inside it has an amplifier with controlled gain. Output will be our signal. I'll connect the cable. Let's use, one second, I want to use this. This is some color. Here. You can see this is our source, our information in a bit different scale. You can maybe not the best, but you can see it's 100 kilohertz. And we have this 100 kilohertz, but amplitude is changing as a transferable signal. See my information. I'm transferring very simple signal. 1 tone at 1 kilohertz. I don't know. I can connect an amplifier to make it hearable. I'm transferring 1 kilohertz, and you can see 100 kilohertz with the amplitude is subject to sine, and here we have info encoding. I'm changing the depth of modulation at some degree will cause disturbance. I can use internal 1 kilohertz. From internal source, it's over modulation. That's over 100%. I can have that over 100% and signal is now it will be corrupted. From the outer source it looks like this. Nice. Modulating signal, 100 kilohertz carrier, and modulated signal. Now the easiest way to demodulate. Circuit like this. And not ideal. Why not ideal? Because not loaded. 1 second. Don't like it. The stem. Not the best one. Switch to lower frequency. Not ideal, but something. something needs to be filtered. Okay, I'll switch back. Higher quality can be achieved with the help of so-called synchronous detector. The signal is multiplied with the signal local generator, but synchronized with the carrier. Okay, it's not so important. I would like to show the signal on a frequency. Okay. I would like to show signal at the frequency space. Oh, here it is. The red line, our modulated signal as a function of frequency. We have central element or central band and two side elements. Where is my let's take a look. The central one here, 100 kilohertz, it's our carrier. And sides, this one, 101, this one, 99. Looks like it's our signal, it's our info. Let's share it. Central remained, these two near disappeared. How they're growing. We see an interesting thing about amplitude modulation. Transferred signal, that's what we'll go to amplifiers and to antennas or to cable, contains now 3 elements or occupies 3 frequencies. Central one, carrier, and 2 sidebands. Upper sideband and lower sideband. I have added third harmonic at 3 kilohertz. Look. Central 100. Base harmonic of my signal 101. And this one 103, third harmonic. What do we know? A rectangular signal can be approximated as a 100% of first, 1/3 of a triple frequency, and 1/5 at 5 times. Quasi-rectangular signal, central band, first harmonic, 100%, 1/3 of the third harmonic, and 1/5 of the fifth, 105. We see what signal spectrum of amplitude modulated signal is formed central band carrier not carrying any information. In fact, this is useless. And signal spread symmetrical relative to central frequency. See what's going on? In fact, we have the same, I don't know, it's voice, anyway, it's the same information transferred in two frequency bands. One, this central part is useless. It's not carrying any information. It's just based on energy, in fact. Useful information spreading to upper sideband, and the same as mirror to the lower sideband. In fact, only this part will be enough for information transfer. So if we have transferable with a spectrum, I don't know, something like this, we will see what? Omega 0 carrier, one spectrum of and mirror it. Maybe better. And the same spectrum of omegas. In fact, only one. This will be upper sideband, lower sideband. Central is to save energy. It may be preferable, and it's often used, not to transfer the central frequency. It will be balanced modulation. Also, transferring both sidebands, they contain the same information. So, SSB modulation can be used. We can transfer only lower or only upper. I'm not sure. I can try to get it in reality, but I'm not 100% sure. It all depends on the air. I'll try to, I have a receiver with signal, internal signal connected. We can try to see how it's in reality, but not 100% current. This one works stable. But with the air signals, sometimes it's okay, sometimes not. Let's try to get real air signal. First I need an antenna cable. can try. And one. Oh, Manuel, respect, that's okay? What do I need? Yes. I need a green box. Filled and funky. See. Old military receiver. I'll take it from the box. Here it is. You can feel the spirit of the 50s. Oh no, it wasn't a good idea. It definitely wasn't a good idea. 1 second. I'll fix my mistake. I want to put an earth cable. The earth cable has a bit different view. Okay. Now, what I need a power supply. I didn't manage to get original one, they're quite rare. So I'll use this cake. I called such thing cake supply. Ground to the ground. 1 voltage. Second voltage. And then connected. And where is my speaker? This one. Let's see who's alive now.
What does it talking about?
I don't know, okay. Anyway, it's a signal. How such receivers work? How such device work? Antenna signal goes through amplifier, then filter with controllable F0. Later, the most interesting part, generator called heterodyne with a frequency, let's say F0 plus FE or F0 minus FE. FE is called intermediate frequency. Resulted signal goes to filter with a fixed intermediate frequency. Spectrum of received signal is transferred to the frequency of the processing, to the processing frequency, and then processed with a series of filters and amplifiers at one amplifier, maybe more filters and more amplifiers. Spectrum is transferred with help of heterodyne to the one for all receiving frequencies. Processing is, let's say, is carried on a one frequency called intermediate frequency. And this one has one. More advanced models has up to perform up to 3 conversions. So they have 3 different intermediate frequencies. This one has only one intermediate frequency. Processing with a filter. Detection, amplification, so what may be special I'm changing the passband of the internal frequency. It has ability to change passband of the internal frequency filter. For, let's say, telegraph signal, only narrow band is needed. So the narrowing band, the less influence from the outer disturbances. But less information can be fed. For telegraph, only 300 Hz are needed. So I can use very narrow band, but well, narrow. Full. But well protected from outer disturbance. For voice, wider band is needed. For example, for standard VGA video requires 6.5 MHz. Voice with good quality prefer 1 kHz. For protection device, 48 kHz. Yeah, what I want. Scope of processing and intermediate frequency. I can attach a scope somewhere here. Into the intermediate frequency network. We see an intermediate frequency signal. Should be 460, but I don't know, it's a scope error, or there is a bit difference. So, station transmits at 18.5 megahertz. This frequency is 11.5 megahertz. If intermediate kilohertz. a signal at intermediate frequency. 1 second, I'll take another wire. I'll get this one at a low frequency. I just need a second. Here it is, sound received and signal at intermediate frequency. And what about spectrum? Moment. Here it is. See, bit asymmetric. This way back. Limited on one side because I have this reception window shifted to the one side. That's why we saw unsymmetric spectrum. Now I'm adjusted resulting reception window as it should be, and we can see nice symmetric spectrum around the central of intermediate. It's intermediate frequency. I'll measure it. You can see it's F. We got problem. See what the problem is? I'm above Nyquist frequency. But it's not enclosed in F. One second, I'll turn camera.
hani çok ciddi cihanet yaşandı. Tüm Ruslardan azimde, tüm Murat'ın Rus ağabey, şöyle nazar olan da sevgiyatırın. Gav aldı bir Afganistan hati arasın, yani sadece kışlandığına Amerika'ya, Rus'a, İran'da Hezeki Taliban, Nihari, o terör darbat yürüyor. Acı bir gavin
Signal, received signal at intermediate frequency, demodulated signal, and spectrum at intermediate frequency. Carrier now at intermediate frequency. And our information, our voice. And now I can, no guarantees at all, I will try to find a single sideband signal. This one is usual amplitude modulated. I would like to see for SSB. No guarantees at all, I may found it when I'm possible to find and possible not to find. Oh, see, I cut the passband. See, only low frequency remained. Full spectrum, truncated spectrum. Only low frequency remained. But I need this one is useless. Let's try to find something. It's extremely disturbing. Problem, we have a lot of computer equipment here and terrible level of noises. Only very strong transmission can get through. They Yeah. CV. The central one is our intermediate. Come on. See, where the signal appears. LSB. Guy use LSB transfer. I have switched off so-called telegraph heterody. Problem with SSB signal. You see his signal appears, but we can't hear anything. Why? Because without the central frequency, it is not possible to demodulate it. It's incomplete. Transfer happens. You see. But we need to recreate amplitude modulated signal with addition. This central line, it's a local so-called telegraph heterody. To demodulate SSB signal, we need to recreate the central band. Without it, it's not possible to demodulate. We don't know where to put this part. Information is here. I have switched off the telegraph heterody. Something gets transferred, you see. But we can receive it. Because we don't have the central.
So it's used to save costs from transfer.
Yeah, it's saved in measures of energy. SSB yields 16 times more effective. You can reach the same distance with 16 times less powerful transceiver. For example, to communicate with Italy, AM requires at least 200 kilowatt peak power. SSB 200 watts. Maybe I can find. It's problem of local disturbance. Come on, you telegraph guy. Come back. Nothing. Even Doomsday buzzer. It's a data flow. Frequency 10011100009111. Also SSB. See? Spectrum signal is itself, but we don't hear. Add local heterodyne, and here it is. 10010009. I'm shifting frequency relative to telegraph heterodyne. Hey, come on, come back. Damn it. Why they cut transmission? Without telegraph heterodyne. Now I had local signal. You can hear. We need decoder. The result will be data flow. 1009. Decrypt it. And get the result. Possible nobody from prosecutor office came for you. 100% it's a military. Нет. Все закончил.
Сделали?
Да.
Отправили им?
Нет, то есть я там же выложил, у него уже есть уже доступ.
Так она же не знает.
Ну так с ней надо сейчас закончу поговорить. Тут жизнь, да? Nobody here. What can I do? No. No luck. Empty carrier. Again empty carrier. Yeah, it's much easier with amplitude. No human, only machines. These are humans. Standard AM signal. Central and symmetrical sides. It's disturbing.
Is it possible to
Need
use?
a good reception, go far from computers.
Is it possible to use TV antenna to receive the signal?
Yeah. Also, modern TVs use digital. No luck. Larger antenna and far from, as far as possible, from digital equipment. And these lamps also, they have electron ballasts, also produce terrible noise. Now put receiver in the box. This will bit reduce noise level. This one is field version. It's not so sensitive. It is very hard to get something from nothing. Or shell helps a bit. It's a telescope. telegraph channels, they are across. Working. Because of small frequency band and low data rates, they can survive, telegraph channels can survive terrible noises. Someone practicing. No humans. Okay, I think it's enough for today.
Are telegraph signals only in amplitude modulation?
No! Telegraph signal use as usually they work in a single sideband. Or telegraph may telegraph may use FST, frequency shift keying, but these all are they all work with single band. Actual telegraph, not wasting energy. Frequent transfer, no transfer, transfer, no transfer, transfer, no transfer. 100% is used for let's say 100% is used. While on amplitude modulation, 3/4 are lost. But it's cheaper, receivers are cheap. And equipment, broadcasting equipment is cheaper. Next time I'll get FM signal. It's much more complex. Rare day when I get single sideband without problems. Usually it's Saturdays, it's this part-time group. Need a better receiver. To keep it, we saw data and telegraph. Not zero.